Hi, we're gonna do question 3 on the series of magnets and currents questions. And question 3 has this drawing that you see in front of you. It looks really complicated, but it's not really. And they give us this, and they say the figure below shows a circuit that includes an electrical relay used to switch on a motor M. So that's the motor M, and the diagram is labeled with a few things. One of the things is here. It says springy contacts. So these are the contacts, and springy means that they are mounted on some kind of spring. And they then label this as the ion, soft ion, and they label this coil. Well, that's the coil, and this is the switch S. Okay, and the question then says, explain in detail how closing switch S causes the motor M to start. Okay, so a relay circuit is a circuit that is used to switch on another different circuit. So normally the secondary circuit, which in this case is this one over here with this motor, will have a larger current, and the one that you use to actually start that second circuit will have a smaller current. And very often they have an electromagnet like this one in order to do that. To explain what how this occurs in some detail, so let's talk about this a little bit, and you can take notes as you go as I speak, because I'm not going to write it all out. That would be very time consuming, and we want to go over a few questions in this video. Okay, so what happens when we close this switch here? When we close this switch here, this is the positive side of the battery here, and so the EMF of the battery will produce potential difference that will get the current flowing in this direction. The electrons actually will go in the other direction, but the positive conventional current will go in this direction. And as that happens, as the current and the charges go around the coil here, around this soft ion core, well, with any coil you will get a magnetic effect where you get a north pole and a south pole. Now here the cable goes in front, the wire coils in front and then in the back, and then here in front and then in the back. It's not very well drawn, but it goes like that. And the if we wanted to know which pole is which, we would just look at it from the sides. And the trick is, for example, if we were looking here with our eye in this direction, then we would see the coil go like that, and the current would go like that and in there, so it would go like that, right? So up here and then down here. And whenever we have this kind of rotation, which is anti-clockwise, then imagine drawing an N or drawing an S. Okay, if you drew an S would look like this. So that's how it should be going if it was an S, which is clockwise, but it doesn't go like that, it goes the other way. So this tells us then it's the north pole, because the north goes like that, up there and down here, and that's what's going on here, up here and then down here. So we know that the north pole would be this side here, and the south pole would be that side there, right? Not that that's so important here, but it's just good revision to know that. And what else? Let me delete this. What we do need to mention is that the soft ion core here will increase the magnetic effects that this coil has, and when this becomes magnetized, which will happen when you close this, then that will become a magnet. It's an electromagnet, so it's only switched on for when the switch is closed, and when you open it again, then the electromagnetic effect is lost. But while it's magnetized, this is a south pole. Since this is a pivot and this thing here is free to rotate one way and the other, then this will be magnetized. So that's a south pole, this will magnetize the soft ion here, and you will get a north pole here, and there will be an attraction between these two poles. So this will rotate in that direction, and therefore, since this is a solid piece of iron, that will rotate in that direction, and it will push this springy contact up here until they touch, and then this current will start, and it will keep on going for as long as this is switched on, because this is not going to be changing direction. That's going to stay with this attractive force, and therefore that contact is going to stay there. The moment we switch this off, then since this iron is a soft magnetic material, this will lose its magnetism. This will pivot back to its place if it's got a spring that will ensure that that happens, and that's why these are springy contacts. Also, the spring wants to put these apart, so the moment that this force is no longer pushing up, the spring will re-establish itself, and these contacts will come off, and then the motor will be switched off. So that's how a lot of buttons for switches actually work to activate and deactivate certain circuits, and hopefully that makes sense. So that would be, if you explained all of that, you would get absolutely full marks, and you can do it in stages. Okay, so first you explain that this will be magnetized, then you can explain that whatever pole is here next to the soft iron core, the opposite pole will be induced in it, and therefore there will be an attraction, and that will move sideways. This will move up, press the contacts, and this will then this current will start flowing, and the motor will go on. Okay, so this type of circuit is really called a magnetic relay. So if you get asked for what a magnetic relay is, then you can say it's this. Okay, so here's the next question. Apologies for the bad drawing, but imagine that's a magnet and it's curled like that, so that there's a gap in the middle between its own south and north poles, and there's a wire that goes across it. And I haven't drawn the rest of the circuit, but imagine there's a current flowing through it, so it would be a complete circuit. The question says the diagram shows how a long wire placed between the poles of a magnet. When current I flows through the wire, a force acts on the wire, causing it to move. So this wire is going to move in some direction, and in part A they ask us to use Fleming's left-hand rule to find the direction of the force on the wire. Copy the diagram and show the direction of the force on your copy with an arrow labeled F. Okay, so it's very hard to draw a hand like this in 3D, or at least for me, but whenever we're trying to calculate the force and the direction of movement of a wire, we always use Fleming's left-hand rule. Left-hand rule. So that's for calculating forces and thrusts and directions of movement on wires when they go through a magnet. But when we want to calculate the EMF generated in a current due to a change in magnetic field, then we use the right-hand rule. So remember that whenever you're talking about generators, you have the right hand. So it's important to generate electricity. So I always remember it like it's more important to generate electricity than anything else. So then the right-hand rule, which is my main one, would go with the generate. If you're left-handed, then you might consider that moving a force is more important. But left-hand rule then is for calculating forces on currents and wires. So here, if we use the left-hand rule, then the rule was that the first finger, or your index finger, is first finger field. Right, so this tells you should point that in the direction of the magnetic field. Okay, and the magnetic field always goes from north to south when you're outside of magnets. So the magnetic field here points down, like that. The second finger, the big C stands for C for current also. So second finger current direction. So your hand should now be pointing with your index finger downwards straight, and your middle finger should be pointing in the direction of the current. And if you're using your left hand, then your thumb, the th is also for thrust. Thumb and thrust, or force, which is the same thing, that will be the direction of the force. So if your index finger is now going down and your second finger is for the current going that way, then your thumb should be pointing basically kind of into the screen in that kind of direction. So the force should be really going in that direction. And that's if this is the situation, then the wire will move like that, will move that way. Part B asks, explain what will happen to the force when the wire force on the wire if the current through the wire is increased. So if the current is increased, then the force will be stronger, so it will move in that direction even more. Okay, so here you can say the force would be stronger. If the current increases, the force is stronger, so the wire would move more. In the third part of the question, part C, they ask us, part B has several parts, so actually that's part B, part 1. B, part 2 says what happens if a weaker magnet is used. Well, if a weaker magnet is used, it moves less. There is less force, and so therefore it moves less. Moves less as smaller force. And in the third part of part B, they say the direction of the current is reversed. So you can check this out with your hand if you want and see what happens. But basically the direction of the current is reversed, and now suddenly starts going in that direction. Then do it with your hand now, and you'll see that. Do it in blue now. This is blue, this is the next part of the question. So if that's the current, then your second finger points in that direction, your field still points in the same direction, and then you see that your thumb actually points, should point in this direction. So try that out please, to make sure that it's all okay. So your field is still pointing down, because we haven't switched the poles of the magnet or anything, we just switched the direction of the current, so it would move in the opposite direction. Okay. And for the final part, part C, it says name one practical device which uses this principle, and it's an electric motor. There's loads. An electric motor does this, right? You get motion, you have electricity running through a circuit, and you get motion from an electric motor, and by doing it cleverly and using alternating current and alternators and all that, you can make sure that the movement happens in a circular way, and then you can get a rotating effect, and you can link that to the wheel, and you can get a little car moving, or a big car moving.